In this lecture, we are going to start our discussion on basic AC circuits. That is to say, we are moving away from just having constant voltage sources and resistors to more circuit components like capacitors and inductors, as well as sinusoidal AC sources. We will start with a very simple circuit and we are going to analyze it in some detail. Most of this is old stuff for all of you. Most of you have already studied this in high school. But it's good to recapitulate these things, and what we will see is that there may be some details lurking here and there which you may have missed in your earlier exposures to these subjects. So, the circuit that we are going to talk about is a very, very simple circuit. It's just an RC circuit, that is a circuit in which a resistance and a capacitance are put in series with each other, and the whole thing is connected across some kind of voltage source, which in general can be time dependent. Right now I'm not saying it's a pure AC source or a DC source or a combination. It could be anything. I'm just saying that some kind of source of EMF is connected between the two terminals indicated, and at this stage, at the beginning at least, we allow this to have an arbitrary time dependence. So of course, there will be a voltage drop across the resistance, VR, and there will also be a voltage drop across the capacitance, VC. And Kirchhoff's voltage law, which applies to all situations, basically because it's nothing but the law of conservation of energy, tells you that VR plus VC is going to be E of t. So that's straightforward. To proceed further, we need to know a bit more about what VR and VC are individually equal to, and we already know that. VR, of course, is simply the current through the resistance times the value of the resistance itself. That's the celebrated Ohm's law. What about VC? VC is related not to the current flowing through the resistance, but to the charge. If there's a charge Q on a capacitor plate, of course, if it's Q on one plate, it has to be minus Q on the other, and the potential difference between the two plates in that case is simply Q by C. Of course, we usually think of capacitance as a capacity to hold charge, so C is the factor by which you have to multiply the potential difference V by to get the amount of charge stored. So CV is Q. Really the V here, we're writing it as Q by C. So this is basically what Kirchhoff's voltage law becomes in our case. I, of course, depends on time, so does Q. I'm going to drop the Q of t, the of t, this bracket t thing, in the next few slides for the simple reason that it's messy to keep on writing. But you have to remember both the charge and the current are in general functions of time. So end up with an equation like this: I into R plus Q by C equals E. But we already know that the current I is related to the rate at which charge is deposited in the capacitor plate. In particular, I is nothing but dq dt. That is because it's the same current I which is flowing through the resistor and into the capacitor. And using that, what we can do is change this equation that we wrote down a while ago into this one, which is clearly a differential equation for the quantity Q. R dq dt plus Q by C is E of t. And with a simple manipulation, it becomes this equation. Now, in this form, it's obvious that this is a linear first order differential equation for the quantity Q as a function of t, and it has an obvious integrating factor, which is e to the power t by RC. I hope all of you remember the basics of ordinary differential equations. This is in fact one of the first kind of non-trivial differential equations that you have ever solved. And you know that if you multiply this on both sides by e to the t by RC, the integrating factor, the left hand side, which is the one which has the derivatives, will become a total derivative. In other words, carrying out this multiplication makes the left hand side a derivative of a single function ddt of q into e to the t by RC. So this is the final form of the differential equation, which can be solved very easily, because the left hand side is a total derivative and the right hand side simply is a known function of time. It's a matter of simple integration from time t equal to t0 to t to give us this result. The left hand side simply integrates directly, and you put in the initial conditions, put in the limits, you get qt to the t by rc from the upper limit, qt0 to the t0 by rc from the lower limit, and the result is simply an integration from t0 to t of the function on the right hand side. All I have done is I have been careful that the variable over which you integrate is really a dummy variable, so I have decided to call it something else other than t. T, of course, here is the upper limit, so I have called that variable t prime. That's all there is to it. Now, this thing can of course be easily rewritten to express q of t as a function of time. So there you have it. The most general possible solution of the amount of charge on a capacitor in an RC network is given simply by this expression, where if you want to know E of t, the time dependence of the EMF, you can evaluate the integral on the right hand side, and once you have evaluated the integral on the right hand side, you have got your final full result for the charge on the capacitor, which in the special case, when E of t is say E0, a constant for t greater than t0. So all we are talking about is at t equal to t0, you have a battery, a constant battery, E0, switched on. Before that, there was something in the circuit perhaps. The capacitor had some amount of charge in it, qt0, and let's go along with that and see what happens. In this case, of course, the integral is trivial to calculate. E0 moves out of the integral sign, so does r along with it, and you are left to integrate the simple exponential, where you remember e to the minus t by rc is just a constant. It's a t prime which has to be integrated over, and now the integral works out to be very simply. This is the indefinite integral that you have. Exponentials, after all, are the simplest things in the world to integrate or differentiate. And once you plug in the initial and the final times, you put in t, of course, at the upper limit, you end up with a 0 in the exponent here. That means this just gives you E0c. Whereas if you put in t0 for t prime, you get a term which is similar to this one. So finally, you end up with this expression, and you can rearrange that, or if you want to, but more importantly, this immediately gives you the voltage across the capacitor, VCT, as this thing divided by the capacitance. Qt0 by C is nothing but the initial voltage across the capacitor, so VCT0. So you get an expression which looks like this, plus E0 into 1 minus e to the minus t minus t0 by rc. Now we can spend quite some time discussing the general nature of the solution and exactly how it behaves and so on, but I'm pretty sure you have covered all this in an earlier class in some detail. The only thing that I'm going to point out is that as t becomes very big, gets closer and closer to very large values, the exponential here becomes very tiny, so does the exponential on this term. So VCT in the long run, no matter what you start from, approaches E0. So this graph shows that this dashed line indicates E0, and here I have assumed that the capacitor was initially uncharged, so VCT0 was 0, but you should be able to easily judge that no matter what your VCT0 is, ultimately in the long run you are going to end up with a potential of E0 across the capacitance. And let me point out, when that happens, the potential difference between the two ends of the capacitor exactly matches the potential which is driving the system, the battery, and hence the two balance each other out. There is no further current in the circuit. simply because there's no drop to be had any longer across the resistance. And this is consistent with the fact that the capacitor no longer charges up or discharges, and you have ended up with a constant voltage across the capacitor in the long run. So this is the steady state which this particular circuit achieves in the long run. There's one thing, if your capacitor had been charged initially to a potential higher than E0, even then the same thing will happen. As you can see, in the long run, VCT0 plays no role, it just dies out. But then of course the charge as a function of time would decrease until it steadied out at E0. I will let you play around with various values of VCT0 and see what the graph looks like in different cases. You can easily do that using any one of the graph plotting softwares you have learned so far. But no matter what you do, in the long run here, something very simple happens. You end up with a steady state at a constant voltage. Once the capacitor balances out the battery, that's it. Well, let's move on to a slightly more interesting case or non-trivial case where we assume that the EMF source is not a constant, as I did in the last example, but a sinusoidal function of time. So this, of course, was a general result that we had derived. Now, let's assume that E of t is E0 cosine omega t plus phi 0. So that's something which we have to plug in here. And if you had paid attention to your class 12 level integral calculus, it's pretty simple to work out this integration. This is a standard integral which requires a couple of steps in between and so on. And this is the integral that you really have to calculate. Well, it's easy to do this integral using standard techniques of class 12, but it's even easier if you do something which, again, most of you already know. Make use of complex numbers to carry out this integration much more simply. What we do is, instead of our real electric field or real EMF E of t, which is E0 cos omega t plus phi 0, we introduce a complex version of that. I'm going to call it E tilde t, put a small twiddle or tilde on top of E to denote that we are dealing with the complex function here. And E tilde t is going to be E0 e to the power j omega t plus phi 0. Just in case some of you are confused by the letter j here is nothing but square root of minus 1, which we usually call I in complex algebra or analysis. In circuit analysis, unfortunately, I is already taken by something much more important for us, that is the current, which is why we go in for the next letter. So that is a standard convention. Whenever we are dealing with circuit analysis issues, J is what stands for square root of minus 1. So E0 is a j omega t plus phi 0, and where E0 of course is the original amplitude, a real number. What we can always do is define a complex amplitude E0 tilde by including e to the power j phi 0, the other constant term in this expression, along with E0 and making the whole thing a complex amplitude. So we have E0 tilde to the j omega t. Why do we go in for this form? Because E0 tilde to the j omega t has a real part which is exactly E0 cos omega t plus phi 0. So ultimately, instead of doing this integral, which is slightly complicated, although I did say it's a class 12 level integral, it takes some amount of work to work this out. It's much simpler if instead of the cosine you had an exponential. As you realize, an exponential is much easier to integrate. And we get an exponential. The cost is you have to deal with complex functions whose real part is the actual result that you want. So the second term here simply becomes the real part. This symbol here stands for the real part of this integral E0 tilde by r, the integral from t0 to t of e to the power j omega t prime. Notice E0 tilde to the j omega t prime has a real part which is exactly E0 cos omega t prime plus phi 0. along of course with this e to the minus t prime by RC, which of course is a real function anyway, which by the magic of exponentials just adds up to the exponent there. So now you have a nice and simple exponential integral to calculate. And this calculation is nearly trivial, so I don't really need to explain this to you. Just to point out that the coefficient of t prime, which in the exponent, which is the one thing which is being integrated over, is j omega plus 1 by RC. So you simply have j omega plus 1 by RC to the power minus 1 times the rest of the integral to be done. E to the minus t by RC is just a constant, and this is the integral that you have, and you put in the limits, upper limit t and lower limit t0. And again, this is something very, very simple. It's of course easier to follow this if you are actually using pen and paper and working it out on the side. And this is what the integral works out to be after you put in the upper and lower limits. E to the j omega t minus e to the j omega t0, e to the minus t by t0 into RC. So after we calculate all this, we still have to take its real part. And this is the full expression for q of t once we bring in also the first term, q of t0 to the minus t by t0 by RC. So this is my final result, but I can make it easier to understand just by noting several points. Firstly, I have deliberately written two terms here in red, and it should be easy for you to guess what these two terms really mean. These are the terms which have exponential minus t by RC terms in them, which means that when t becomes very, very large, these terms are going to die out. So these terms which are marked in red die out with time. In the case when which we dealt with earlier, we also had terms like these which would die out over a long time, and there ultimately we had a steady solution when you left out these e to the minus t0 by RC terms. And that steady solution, in that case, was just a constant voltage. Here we are going to get a different steady state solution, because after the terms marked in red die out, we will be left with this expression which still depends on time. So as time becomes very, very large, so you have to realize that when we say t approaches infinity, all we are really saying is t minus t0 is much, much bigger than RC. Which is when the exponents in here are very, very large negative numbers, and if you exponentiate and with a very large negative number, you are going to get something which is very small. So here t going to infinity really means t is much, much bigger than t0. How much bigger? So much bigger that t minus t0 by RC is a number which is much larger than 1. So once steady state is reached, the voltage across the capacitance is simply what you get when you divide this whole thing by C. That's always true, but we have also taken the advantage of the fact that these terms marked in red die out in time, and we are left only with this expression. So this is a steady state version for the voltage across the capacitor. Of course, we can use simple complex analysis to go further. We can use the fact that 1 plus j omega RC can be expressed in this magnitude phase form. This of course is the magnitude of 1 plus j omega RC. Tan inverse omega RC is just the phase term. So R to the I theta form or polar form for a complex number, that's what we have used here. And if you use this and do a very simple manipulation, you will realize that the E0 tilde is E0 to the j phi 0. So if you combine all the e to the j terms together, I made a mistake here. I forgot that I am using electrical convention. So this I is really j. So once we put that in, I get E0 square root by square root of 1 plus omega RC whole square, which is just coming from the magnitude E0 of this and the magnitude of this. And this entire exponential is about j omega t plus j phi 0 minus j tan inverse omega by omega RC. The minus sign comes in simply because this whole thing is in the denominator. you have an exponential of that, and when you take the real part, it becomes a cosine. So we see several things. First of all, the voltage across the capacitor is also sinusoidal in the steady state. In a given finite time, of course, it's much more complicated because it has contributions from this term and this term. So these steady state, these terms in red, but they will die out. These are the so-called transients. We will pay more attention to them later. But these are things which stay only for a small time after you start your circuit. In the long run, they die out. So much of what we will discuss will be based on the steady state solution. What happens after a long enough time has elapsed? Here, what happens after a long enough time has elapsed is VCT becomes this nice sinusoidal function. Remember, the original input voltage to the circuit was E0 cos omega t plus phi 0. Here, we have a fraction of that as the amplitude of the voltage across the capacitor. That sort of can be understood because, after all, current has not dying down here. We have just reached a steady sinusoidal voltage, sinusoidal change in the charge, so sinusoidal current. Hence, a drop across the resistance, which also is non-zero. So a fraction of the voltage is dropped across the capacitor. But what is also very interesting is the time dependence here. The time dependence of the input signal was E0 cos omega t plus phi 0. Here you have cos omega t plus phi 0 minus tan inverse omega RC. What this means is that there is a sort of time lag between what happens at the input to what happens at the capacitor. Say the input peaks, let's say, when cos omega t plus phi 0 reaches 2 pi or multiples of 2 pi. The capacitor voltage peaks, on the other hand, when omega t plus phi 0 minus tan inverse omega RC matches the same multiple of 2 pi, which means because of this presence of the minus tan inverse omega RC term here, this happens at a slightly later time. You need a slightly bigger value of t to compensate for this negative term which is sitting here. So what that means is the input sinusoid, of course, keeps on going up and down, reaching a peak and hitting the trough and going up and going down again. The same behavior is seen for the capacitor voltage, but at a slightly later time. You need t to be slightly bigger for this to happen. So this is what we mean when we say the capacitor voltage lags behind the input voltage. In other words, if you have a phase shift, if the phase shift is negative like this, you have a lag. If for some other circuit you have a positive phase shift, that will be a lead. That means, with a positive phase shift, if this term had been positive instead of negative, you would have needed slightly smaller values of t to hit the same values of phase. So the peak and the trough would have come a bit earlier. So in this case, our terminology is the capacitor voltage lags behind the input. And we can make it slightly fancier by introducing this notation. RC is 1 by omega 0 and express everything in this neat all dimensionless form. Apart from E0, everything else here is dimensionless. 1 plus omega by omega 0 whole square is dimensionless. Omega t, of course, is dimensionless, so is phi 0. And here the phase term has been written down as tan inverse omega by omega 0. We will have more to say about this in a later lecture, the precise form which this takes and what does this imply and so on. Step back and look at what we have done in general. Our system obeys linear and real equations. Linear equations with real coefficients. Of course, they are linear differential equations, but in general they are linear and real. And as a result, we have this huge advantage. If a complex valued function were to satisfy this equation, then so would the real and imaginary parts. And this is very important. We will keep on using complex functions for currents, voltages all the time in our calculation. as we did a while ago. We talked about this E tilde t. But you realize that we really never meant that the actual voltage or current is complex. We meant that this is just an aid in our calculation. We will do the calculation using these complex numbers simply because the calculation is much easier using complex numbers. But in the end, we will take real parts or imaginary parts, as the case may be. What is important is if a complex function is a solution to our system of equations or single equation, because the equation is linear and real, its real and imaginary parts are both solutions. Just to contrast this, the Schrodinger equation in quantum mechanics, I mean the full Schrodinger equation, the time-dependent Schrodinger equation, is linear, but it is not an equation with real coefficients. You have IH cross del psi del t. As a result, the wave function psi of xt, is actually a complex function, and its real and imaginary parts do not satisfy the Schrodinger equation. In quantum mechanics, complex numbers that you use are inherently part and parcel of your system. You have to deal with them. You can't take the real part or imaginary part at the end. On the other hand, in situations like this, in circuit analysis, for example, we use complex analysis all the time, or complex numbers all the time. In electromagnetism, we also do that for the same kind of reason. Use of complex numbers to deal with physical phenomena is all pervasive in advanced physics. But in most such situations, what we are relying on is something like this. Our system obeys, in many cases, linear and real equations. So if a complex function is solution, so is the real part, so is the imaginary part. So what we will do is we will work with the thing as if our electric field or EMF or the voltage across a capacitor or whatever, or currents, these are actually complex functions of time. But at the back of our mind, we always know that in the end, we can take the real part. And in the end, we will take the real part. Sometimes we will just omit mention of the fact that we are taking the real part. We might even say our final capacitor voltage is this complex function. But you have to realize that we always know that the actual voltage across the capacitor is the real part of whatever complex function you're talking about. So let me stress once again, we are going to work with complex potentials and currents, but with the understanding that in the end, we might say the potential is this complex value or the current is this complex value, but we always mean take the real part. So with this understanding, what we will do is we will drop the tildes from our notation so far. We wrote E tilde t to indicate that that really was not the EMF. It was not E of t. E of t was really the real part of that E tilde t. But we will not do that any longer. We will just say that this complex voltage or complex potential difference, these are the actual voltages or potential differences or currents as the case may be. Once again, with the understanding that the real current or real voltage, etc. are all real parts of whatever complex functions we have. So what we will do is we will say that the voltage across the capacitor is a function of time given by the complex E of t. This E of t is now what we used to call E tilde t earlier, divided by 1 plus j omega RC. Okay. So just one more time for emphasis. E of t here is a complex function, and because of the presence of 1 plus j omega RC, it's obvious that VCT is a complex function. The actual potential across the capacitor is a real part of whatever this is going to be. But now we see that we can write this also in this form, 1 by j omega c in the numerator plus r divided by r plus 1 by j omega c in the denominator times E of t. Now this should remind you of something very familiar from high school physics. For two resistances R1 and R2 in series, then the potential drop across R2, if the drop across the entire thing was E, would have been R2 by R1 plus R2. into E. That's the potential division formula for a series circuit. This looks exactly like that, except that if you want to call this the series potential division formula, you pretend that the capacitance C has a quote-unquote resistance, which is 1 by j omega C. Now, of course, you cannot call this resistance. It's entirely different. So we use a general name for this. We call this an impedance. The impedance of a resistor is resistance R, but the impedance for a capacitor, ZC, is 1 over j omega C. Again, this should all be very familiar stuff for all of you, but a recapitulation never hurts. So, where does this 1 by j omega C really come from? You can think of this as something which comes from the so-called Ohm's law for capacitance. There is really no name for this law. You have Ohm's law, which relates the current through a resistance to the voltage across its two ends. The voltage across the two ends of a capacitor, of course, depends on the charge which is there on its plates, and that law, I'm just calling it Ohm's law for capacitance for want of a better name. So we start with the fact that the voltage across the capacitor is a complex sinusoidal function. So V0 tilde is a j omega t, where V0 tilde still has a tilde on it, just to remind you that V0 is not necessarily a real number. This V0 tilde is a complex number which, in addition to the amplitude V0, also has a phase, whatever phase the capacitance voltage has. Now, if this is VCT, the charge across the capacitor plates is just the capacitance times this, and the current is nothing but its time derivative. Now, if you differentiate this quantity, j omega will come down. That's all that happens when you differentiate an exponential. So you'll end up with j omega c times this V0 tilde to j omega t, which I've deliberately coupled together with an underbrace here. Why? Because this, of course, is nothing but Vc of t. Unfortunately, the rest of the formula has gone out of the screen, so you can't see it, but this really is all that matters, is j omega c times Vc of t. The of t is off screen somewhere. So once you have the current voltage relationship but this of course only works for sinusoidal currents and voltages, but that's the situation we are going to deal with most often when we are talking about AC circuits. Once we have this, we can easily define the impedance of the capacitor as the ratio between its voltage and its current. Again, ratio between its complex valued voltage and complex valued currents, and that turns out to be simply 1 by j omega c. Okay, so that's all there is to it. You start with the complex valued voltage, you calculate the charge across the capacitor, hence the current, hence the impedance, just by dividing. Now, if we use this idea for our RC circuit, we have just drawn the RC circuit slightly differently. This form just emphasizes that we want the voltage across the capacitor to be the output to our circuit. But notice that if we think of the current as a complex valued function, we can draw the current both as a point on the complex plane or as a vector joining the origin to that point. Then, if the current is a complex number, which in this case I have just indicated as a horizontal line, so maybe at some particular time t the current just is real, when the total phase is 0 at that instant of time, then the voltage across the resistance is simply going to be the R times that, R being a real number, is going to be a complex number or complex vector indicating that complex number in the same direction. What about the Vc? Vc is I, the current, divided by j omega c. Now, because j square root of minus 1 has a phase of pi by 2, j, remember, is exactly to the j pi by 2. Division by j essentially means it's rotating the thing by pi by 2. So, I'm pretty sure most of you remember this. If you multiply a complex number z1 by another number z2, What happens to the number z1 or the point representing the number z1 is, first of all, it gets rotated through the phase of z2. It also gets scaled by the magnitude of z2. So here the size of Vc is set by this factor 1 by omega c, and the fact that there is an extra j here means that it's going to be exactly 90 degree behind I, or behind the terminology which will become clear when we talk about how this thing changes with time, but it's going to be 90 degree below the current and the voltage of the resistance. So what about the sum of the two, which is the overall EMF input to the circuit according to Kirchhoff's voltage law? As you all know, to indicate sum of two complex numbers, you need to use the parallelogram law. Basically, or more precisely in this case, just the rectangle law. You draw a rectangle with VR and VC as two sides, and the diagonal gives you VI, the input voltage. And these two angles are really the critical things here. Theta C is the angle by which, or the phase angle by which, the capacitor voltage lags behind the input voltage. Theta R, indicated in red here, is the angle by which the resistors, the voltage across the resistance, leads the input voltage. So in this case, of course, the voltage across the resistance and the voltage across the capacitance together make up the input voltage, and the capacitor voltage, as we already indicated, lags behind the input voltage, and the resistor voltage makes up for that by leading the input voltage. So what does this mean in terms of how things change with time? So let's now try to figure out what will happen as time evolves. As time evolves, because of the e to the j omega t factor, which is present in each and every one of these things, I, VR, VC, all of them are going to rotate around at a constant angular velocity omega. And so this is what's going to happen. Okay, there are plenty of things in the graph, so maybe let me just indicate what these things are. The color coding is like this. The orange one is going to indicate the voltage across the resistance. The green one is going to indicate the voltage across the capacitance, and the blue one is the total or the input voltage. So at the beginning, we are assuming that at the instant of time which we have chosen here, the current is at zero phase, so current is at its peak, so is the voltage across the resistance, and the voltage across the capacitance is just zero at that instant. So my point, the blue point which indicates the total voltage, is sitting here, and as I go around, let's see what happens. The red point indicates, so here the blue point indicates the total, the voltage, red point indicates the orange point indicates the voltage across the resistance, the green point indicates the voltage across the capacitance. And these are the actual real values of the voltages which are being plotted along the screen, and it's going to go back and forth. So these are the projections along the real axis, the real parts of the complex numbers. As you can see, as things go by, this is how the things are changing. Let me just indicate that this is the total voltage. It peaks at this time t here. Orange indicates the voltage across the resistance that actually peaks a bit earlier. That's what lead means. And green, the voltage across the capacitance, peaks later. That's what it means when you say it lags. Now, all that I have told you so far in this lecture has been old stuff. You must have met this in your high school days, if not at least in differential equation courses in the last 2 years somewhere. What I'm going to tell you now may be slightly new to you. It's not a very unusual or new thing that I'm talking about. It's just that you may not have been exposed to this as yet. So this is the use of the Laplace transform in trying to solve the same problem that we have been trying to solve so far. So before we do that, let's talk about why would we want to learn a new technique at all. Now, if the steady state behavior of a circuit is all you want to know about, that is, once the transients, once the initial fluctuations have all died down, the thing settles down to a nice steady state and that's all you ever wanted to know about, then using complex impedances works fine. However, this will give you no information whatsoever about what happens when you just switch on a circuit. The initial fluctuations which die down, and that's why they are called transients. The transients may really be very important in discussing the behavior of a circuit. Using complex impedances, while a great tool and while making life a lot easier when you're dealing with AC circuits, tells you nothing about the behavior of the transients. Now, for some applications, both steady state and transient behavior of the circuit may be important. Of course, you can always do one thing and just write down the original differential equations. This one that we worked out in this particular video was pretty simple. However, for a more complicated system, it may end up being a very, very difficult task. Even writing down all the differential equations properly may become difficult and solving them may be even more difficult. But that's of course always one option that you have. You solve the original differential equations, putting in all the initial conditions. That should give you definitely a full picture of what's happening. What happens at the very beginning and then what happens in the long run. Of course, that is exactly what we did at the very beginning of this lecture. We started with an RC circuit. We wrote down the differential equation. We solved it for an arbitrary initial condition. Now, it's much easier, of course, to solve algebraic equation than differential equations. This is something you would all agree upon, I guess. So the question is, can I somehow get the same information by solving algebraic equations? The answer is yes, in a way. You can use this trick that we are going to talk about, the use of the Laplace transform, to convert a differential equation into an algebraic equation. And then it becomes very easy to solve. So the Laplace transform is a tool that can help you in this case. So what exactly is the Laplace transform? Well, I'm going to give you a very quick and dirty introduction to the Laplace transform here. There are lots of mathematical subtleties and other stuff which a full-fledged mathematical physics course would go into. I'm just ignoring some of the subtle points. And of course, in this lecture, or whatever is left of this lecture, I will not give you a full-fledged description of the Laplace transform method. I'm just going to indicate the very basics. And what I'm going to do is I'm going to just give you enough information so that we can completely solve the RC differential equation or RC circuit problem using Laplace transforms. So first, what is the Laplace transform? The definition, of course, is on the slide in front of you. Given a function f of t, its Laplace transform is a function of a different variable s, capital F of s, which is defined via this integral. So in a way, it's very similar to the Fourier transform, but in the Fourier transform, this s, instead of an s here, you have a j omega. That in itself is not a huge difference because s can in general be complex as well. But the other major difference is, in the case of Laplace transform, your integral starts at 0 at a particular finite value of t. So the Laplace transform actually has the advantage that it can capture information about what is happening at t equal to 0. So initial conditions, that's the main thing. Laplace transform has information about that. Now, you might of course be worried about questions like, does this integral converge? Now, you would also all realize that because you have an e to the power minus st, and especially if we assume that s has a positive real part, you will have an exponential damping term, which will make the overall integrand behave much better than f of t as t goes to infinity. So unless f of t is a really badly behaved function, the e to the minus st may tame its behavior and give you a finite integral. So in what follows, we are going to assume that that happens. The functions we are going to deal with will give you nice integrals. Of course, a mathematical phase course would have gone a lot deeper into issues about when does a Laplace transform exist and other such concerns. We will assume that in all cases of interest, at least all cases of interest in this course, the Laplace transform of the relevant function will exist. Now, this is a matter of notation. Capital F is a new function, the function of S, which is called a Laplace transform of small f of t. We often write capital F by curly L acting on F. So curly L, you can think of that as sort of an operator which acts on a function in the t domain, a function of t, to produce a new function, a function of S. And sometimes we will just drop the bracket and write curly LF. Just one important thing, this whole thing, curly LF here or curly L acting on F here, is the name of the new function. Now, one very important result, and the real reason why Laplace transforms are such a great thing in solving differential equations, is this. If you try finding the Laplace transform of a derivative of f, so df dt, of course, from the formula, this is what you would have to do. You have to integrate df dt after multiplying it by e to the minus st. Now, I'm sure that all of you will agree that the moment somebody sees an integral like this, the very first thing you would want to do is you would want to carry out an integration by parts, where e to the minus st will be treated as the first function, the function which you differentiate, and df dt as a term which you integrate. So if you carry out integration by parts, you have two terms. Df dt will integrate to f, that's the integral of the second function times the first, of course with the limit 0 to infinity, and the other term where you have df dt is integral f of t and the derivative of e to the minus st, that gives you a minus s, which couples with the minus sign which you always have in the integration by parts formula to give you a plus term here. Now, it's easy to realize that these terms are things you already know. Now, if you're assuming that the Fourier transform, the Laplace transform exists, that is, this integral actually converges, f of t to the minus st must go to 0 as t goes to infinity. So the upper limit here from the integrated out term must vanish. What about the lower limit? It's simply minus f of 0. So from this you get minus f of 0. And the second term is just s times capital F of s, or the Laplace transform. So differentiation in the t domain essentially translates in the s domain to just a multiplication by s. So Laplace transform of the function gets multiplied by s apart from this minus f of 0 additional piece. So this is the result written symbolically. The Laplace transform operator acting on df dt produces a new function. The entire thing within the square bracket is the label for the function that acts on s to produce the Laplace transform of f acting on s times the number s minus f of 0. So basically all that happens when you take the Laplace transform of a derivative is that you get to multiply the Laplace transform of the original function by s, second derivative by s square, and so on. Of course, what is important is you also have the initial condition, the initial value of f of 0 in this case, initial value of both f and f prime, f0 and f prime 0 for the second derivative, and so on. All of these are already included in the Laplace transform of the higher derivatives. Now, in order to proceed further, we will need to know the Laplace transform of a few simple functions. In fact, most textbooks which discuss these things will give you a big table of Laplace transforms. We will need only 3 or 4, maybe 5 for the rest of this lecture, so I'm just going to quickly introduce them to you. if f of t is 1, then the Laplace transform is simply the integral of e to the minus st from 0 to infinity. And e to the minus st's indefinite integral being minus 1 by s e to the minus st. It's easy to see that the upper limit of infinity will give you 0. The lower limit will give you minus 1 by s. So just 1 by s. Of course, in order that this limit exists, you must ensure that the upper limit gives you 0. E to the minus st does die out to 0 as t goes to infinity. For that, you need the real part of s to be positive. That's a condition under which the Laplace transform will exist for small f of t equal to 1. Now, another important and useful case is when f of t is an exponential. I've deliberately written e to the minus at, because if I do that, then the integrand for the Laplace transform becomes e to the minus st times e to the minus at. So all that happens is s gets replaced by s plus a. So the Laplace transform is simply 1 over s plus a, with the condition, of course, that the real part of s plus a must be positive. Well, what about e to the j omega t? That's not a new result. I just can get that by putting a equal to minus j omega in the previous expression. Of course, j omega has no real part. So real part of s minus j omega being greater than 0 is exactly the same as real part of s being greater than 0. So this is not a new result. It's just the same as the previous one, with a getting replaced by minus j omega. But the reason why I'm doing this is that now if I take the real part and the imaginary part of this, I can immediately write down that f of t equal to cos omega t will give me a Laplace transform, which is the real part of this expression, assuming s is real. So what happens when you do that is the real part of this can be found out very easily by multiplying the numerator and denominator by s plus j omega, and doing that is trivial to find out that cos omega t has s by s square plus omega square as its Laplace transform. Again, real part of s has to be positive for this. What about sin omega t? Well, it's the other part, which is omega by s square plus omega square. So these are the Laplace transforms that we will need for the rest of the course, or rest of this, not for the rest of the course, but for the rest of this lecture. In addition to this, we need one more piece of information, which is sort of obvious. The Laplace transform is a linear operation. That is, if instead of f1 and f2, two functions of t, you did the Laplace transform of c1 f1 plus c2 f2, you will get c1 times Laplace transform of f1 plus c2 times Laplace transform of f2. This simply follows from the fact that integration is a linear operation. So armed with this, let me try to solve the RC circuit problem via the Laplace transform method. So we have already solved the differential equation at the very beginning of this lecture. We are just going to repeat the process again, but this time using Laplace transforms. And just to make life a bit simpler for ourselves, let's just choose t0 to be 0 for the time being. That is, the initial condition is given at t equal to 0. This, remember, was a differential equation. dq dt plus q by rc equals the EMF E of t by r. Now, in the Laplace domain, or the S domain, that's technically sometimes called the Laplace domain, what happens is that if you take the Laplace transform of both sides of this equation, the derivatives of Laplace transform simply gives you the first two terms here. Remember, the derivative of q's Laplace transform is s times the Laplace transform of q at s, of course, minus q of 0, plus, and this is the linearity of the Laplace transform in action, plus 1 by rc times Laplace transform of q at s. And that has to be equal to 1 by r times the Laplace transform of the EMF E at s. Now, notice that while you have derivatives, acting on Q, which was originally a function of t, there are no such derivatives any longer. This equation is a purely algebraic equation with LQ of S, this quantity, multiplied by S plus 1 by RC. And you can easily solve this by moving the minus Q0 to the other side and dividing by S plus 1 by RC. So solving the Laplace domain version of the differential equation is very simple. All you need is trivial algebra. S plus 1 by RC inverse times the Laplace transform of E by R plus Q0. Now notice that as far as this equation is concerned, the input here, the source here is EMF of the battery by R. Okay? And the output, what we want out of this equation, is the charge Q as a function of time. Now, while you had a differential equation in the time domain, the Laplace trick has changed that into an algebraic equation in the Laplace domain or S domain. And now what you end up with is Laplace transform of Q essentially is Laplace transform of the input LE by R times something. There's also an additional piece due to the initial conditions, but that's also multiplied essentially by the same something. So this quantity, this function here, which is 1 over S plus 1 by RC, please don't confuse this capital R here with the resistance. That's an unfortunate choice of notation, but capital R is a very standard notation for this function. It's called a response function for the RC circuit. It connects basically the output of the RC circuit, namely Q, with the input, namely E by R. It makes the connection directly in the Laplace domain. The Laplace transform of Q, the output, is exactly equal to the response function into the Laplace transform of the input function E by R plus an additional piece which is due to the initial condition. Now the response function is going to be a very, very important topic in the future classes for more general circuits as well, not only just for the RC circuit. Now let's just quickly use this result to find out the solutions that we had talked about earlier. So we are just repeating problems that we had done earlier. We already know the solutions, but this time we want to find the solutions using the Laplace trick. You must realize that in the Laplace domain we have already found the solution. However, we would usually want Q of t, and for that we have to go back from the Laplace transform of Q to the original Q. That is, we have to do an inverse Laplace transform. Now calculating an inverse Laplace transform is not really that easy. If you take an arbitrary function and you want to find an inverse Laplace transform, you can do that, but you have to sort of carry out rather clever contour integrals over some very cleverly chosen contours and so on. However, it so happens that almost in all cases, the necessary inverse transform can be done by a very, very simple method, which is you look at it hard enough, the answer pops at you. So just by staring at what you need to Laplace transform, you should be able to carry out inverse Laplace transform. Well, there's a bit more to that than just staring at a function, but that's roughly all there is to it, as we will soon see. So, special case, if you have a constant voltage source, E of t is E0. So what about the Laplace transform of E of t? Remember, 1 has a Laplace transform of 1 by s. So E0, which is a constant, has a Laplace transform of E0 times 1 by s, E0 by s. So what is our Laplace transform of Q? All we have to do is, in place of Laplace transform of E, here we put in E0 by s, and this is the expression we have. So now we have to figure out the inverse Laplace transform of the right hand side. Now there are two terms on the right hand side. One is Q0 divided by s plus 1 by RC. The other is E0 by R divided by s into s plus 1 by RC. So let's tackle them one by one. Now the term involving Q0 has a very simple inverse Laplace transform. Why? Because when we worked out our Laplace transforms, the very second function that we had looked at was e to the minus at, and that had a Laplace transform of 1 over s plus a. So here q0 is just a constant, and Laplace inverse, like Laplace being linear operations, q0 will just move outside, and this is just 1 by s plus a. So the inverse Laplace transform will simply be q0 e to the minus t by rc. E to the minus at gave you a Laplace transform of 1 by s plus a. So the inverse Laplace transform of 1 by s plus a is just e to the minus at. And that's all we have used here. Well, now what we want to do is want to find the inverse Laplace transform of this. Now this is a slightly more complicated thing. We have not seen a function like this in our few cases so far. We have seen 1 by s, we have seen 1 by s plus a, then we have seen 1 by s square plus a square plus omega square, and stuff like that. This is s into s plus 1 by rc. So what we do to find out its value is this. You take the e0 by r out, as obvious, and you need to find the inverse transform of 1 by s into s plus a, where a is 1 by rc. How do we do that? Now this is again a place where whatever you learned in class 12 comes in very, very handy. In class 12, you had to do integrals of 1 by x into x plus a or things like that all the time. And the trick that you used there was that of partial fractions. And we fall back on just that. 1 by s into s plus a is very easy to see, has this expansion. 1 by s minus 1 by s plus a, that will give you a by s into s plus a. So you have to have a 1 by a in front. So this is all 1 by s into s plus a is the difference between two functions with a single factor of s down below. And we already know how to inverse Laplace transform both of these. So what is the inverse Laplace transform of this 1 by s into s plus a? Is 1 by a times inverse Laplace transform of 1 by s, which is 1, and inverse Laplace transform of 1 by s plus a here, which is e to the minus at. So that's the answer. So now that we know this, what we can do is plug this here. Of course, here a is 1 by rc, so division by a becomes multiplication by rc, so you end up with e0c outside, times 1 minus e to the minus t by rc. So that's the Laplace transform of the other term. So adding them together gives you the inverse Laplace transform of the right hand side, which is q of t. So q of t is the formula that we had already worked out before, q0 e to the minus t by rc plus e0c into 1 minus e to the minus t by rc. Can easily verify that for t0 equals 0, this is exactly the solution that we had worked out earlier. Well, quickly moving on to the next case. If you have a sinusoidal voltage source, let's say et is e0 cos omega t. We know what the Laplace transform of that is. We figured that out a while ago. Cos omega t has a Laplace transform of s by s square plus omega square. So Laplace transform of E at s is E0 times s by s square plus omega square. If you plug that in our general result, Laplace transform of Q at s is just 1 by s plus 1 by rc times, this is the Laplace transform of E of t by r plus Q0. So how do you figure out the answer here? Well, Q0 by s plus 1 by rc is its inverse transform is something we already know. We had worked it out just a while ago. The new thing that we need has s divided by s square plus omega square into s plus 1 by rc. So let's try to find out what this is going to be. And once again, we fall back on partial fractions. And I'm pretty sure all of you have learned in class 12 how to figure out the partial fraction expansion of this. It turns out to be this particular quantity. So there's a s by s square plus s square term, there's a 1 by s plus b term, and there's a 1 by s square plus s square term. Of course, here a is nothing but omega and b is nothing but 1 by rc. So if you just use that, you can easily find out the answer. I'm not going to tell you all the detailed steps of going from here to here, but actually I've already told you everything. This s by s square plus s square is what gives you the cos omega t, minus 1 by s plus b, the b is 1 by rc is exactly what gives you this, and so on. So these are pretty easy to figure out. I will not insult your intelligence any further by telling you how to work this out. Just pick up pen and paper, write down inverse transforms for each of the terms, taking care that here a square is omega square. But why do you have a single omega here? Because the Laplace transform of sine omega t is omega by s square plus omega square. So 1 omega goes into this Laplace transform here. And of course q0 plus by s, q0 by s plus 1 by rc, inverse Laplace transform. So this I will let you figure out with using a bit of elementary algebra or elementary trigonometry that this result that we have here is exactly the same, at least in steady state, as the result that we had worked on earlier. In the earlier case, we did not bother to write down the whole answer. We did bother to write down the whole answer. We just said that e to the minus t by rc will die out in the long run. So whatever will be left is a steady state solution. I wanted to check that this solution is exactly the same as the one we had worked out earlier using differential equations, the standard way, finding out the integrating factor and all that. So in the next lecture, we are going to take a look at further properties of AC circuits. We will mostly use complex impedances for analyzing that, but sometimes we will fall back on the Laplace transform, especially if you want information about what's going to happen near the very beginning. Note that here, whatever you start at the very beginning keeps on dying down with time, but sometimes the transient behavior may be much more complicated and rich than that. So bye till then. We will meet again in the next video when we talk about other AC circuits.